Okay, welcome to Data Structure and Algorithm. This is CS435 class at Rutgers University, Newark, New Jersey. In these lectures, we're going to cover the concept of, again, binary search tree. We already went through what is a binary tree, and also we give lectures on the concept of a tree data structure. So our main objective is to design and also implement a binary search tree. Also, how to represent a binary trace using the link data structures. Also, we're going to learn how to search an element in a binary search tree, which is one of the main applications in binary search tree. We're also going to learn how to insert an element into a binary search tree, since, again, in binary search tree, elements are arranged in some order, and we shall go through that. Also, we're going to learn how to transverse elements in a binary tree, also how to delete elements from a binary search tree, and also how to display a binary tree graphically. So we start with the definition again. What is a binary tree? Here we say that a list and also a stack and a queue are normally a linear structure or a linear data structure that consists of a sequence of elements. Again, we went through stack and queue and a list. Normally the data are arranged in an order in a linear function. But a binary tree, again, is a higher ranking structure. Normally we have the root node, as you can see an example here. Our root node is 60. Then the root have two children. Again, a binary tree, the most children we can have is 2. So we have the left child and then the right child. And then let's keep going. So this is in a higher ranking form. So a binary tree is a higher ranking structure. Here we say it is either empty or consists of an element called the root, and also 2 distinct binary trees called the left subtree and the right subtree. So here we have 55 here is our left subtree with 55, 45, and 57. Our right subtree will start from 100, 67, 107. The same concept on the right side also. Again, here we can see that the F node have only a left child. Sometimes we may have, example, M node have no children at all. As we said earlier, a node that doesn't have no child is called a leaf node. So again, this is the concept of a binary tree. So these are some few terminologies we should know, the binary tree terms. As we said, the root of a left or right subtree of a node is called the left child or the right child. So if I'm on the root at 60, the left child is 55, the right child is 100. If my root is 100, the left child is 67, the right child is 107. Now, if I'm at 67, it's a leaf node. There's no any child. So a node without a children is what we call the leaf node. And also we have a special type for binary tree called the binary search tree. And this is our main objective for these lectures. So a binary search tree with no duplicate elements has the property that for every node in the tree, again, the value of any node in its left subtree is less than the value of the node. And also the value of any node in its right subtree is greater than the value of the node. So these lectures, again, we are more concerned on binary search tree concepts. So this is an example here. This is a binary search tree. Why? We can see the root is 60. The left child should be less than 60, but the right should be greater than 60. Then when we are at 100, the left child of 100 and the node 100 should be less than 100. The right child should be greater than 100. So this is why we can easily search for an element in a binary search tree, which almost use the same concept of as a binary, or we say the binary search algorithm. Because binary search algorithm, For example, we did that in an array. First of all, the array must be sorted, must be in order. Then we take the middle value, compare the middle with the search key. If the search key is greater than the middle, then we go to the upper side, which will be the right side. If it's less, we go to the left side. The same concept here. If I'm searching for 67, I compare 67 with 60. Oh, 67 search key is greater than 60, so I'll go to the right side. Then I'll compare 67 with 100. Okay, 100 is greater than 67, so I'll go to the left side. So every run we are going to divide. We will not going to go through all the list. We divide it in two. The same concept as again, a binary search tree for searching an element. The time complexity is the same as again a binary search algorithm. So here we said, okay, we have a class named the tree node. Why? Because again, we know a tree normally consists of a node. And normally this is a binary, so we will surely have the left child and also the right child. And so then we have the element. So when we see our diagram here, where the element is, the value is 60, the left is the address of the left child and the right is the address of the right child. So this will be the class for the tree node. Same concept as a stack. When we implement stack as a linked list, we use the linked list consists of node, and we had a node class to use it to create the stack. So the same concept here. Again, this is our constructor, and we initialize the element to 0. Now, searching an element in a binary search tree, as we said, the concept is the same as a binary search algorithm. We normally have the linear search algorithm, which means we start from beginning, search the item, compare the search key from beginning to the end. We don't care about the sorting, the order of the items in the array. Now, when we come to the binary search, we go, first of all, again, as we said the array must be sorted, and we look for the middle, compare the middle with the search key. If it's greater, we go right side. If it's less side, we go to the left. So the same concept here. Now we have the search code here. First thing we assign the root to the current. So the current to be like our pointer that we are going to use to transverse through the binary tree. So here we say we are starting from the root. So we give current to the root. So now first option is that why the current not equal to none, which means we have some node in the search tree, in the binary search tree. So why the current not equal to null? We say that if the element is less than current.element, which means what we are looking for is less than the current, then we go to the left side. So we go left. Otherwise, if it's greater, then we go to the right. So we say current.right assigned to the current. Else, the element matches the current.element, then we return true. If it doesn't match, we return false. So again, the concept here is almost the same as a binary search algorithm. First, we check if there's nodes or the tree is empty. If it's not empty, then the search key, we compare, we say the search key is less than the current.element where we are. Then we go the left, since it's less than the root. If it's greater than, then we go to the right. Then when we find it, we return true. This method, return it type is Boolean, so either return true if you find it, or return false if we don't have it. Now, the next is how to insert an element to a binary search tree. Since we know the element in a binary search tree must be in some order. Everything less than the root will go to the left side. Everything greater than the root will go to the right side. So we need to be careful. So here we say that again, if a binary tree is empty, that's the first option. Then we should create a root node with a new element. That means the tree is empty. The first node that goes in will be the root. Otherwise, we need to locate the parent node for the new element node. Now, if the new element is less than the parent node, then we have to assign the left child for it. But if the new element is greater than the parent element, then we go to the right side. So the node for the new element becomes the right child. And that's again, the algorithm. So this is the algorithm to insert an element to a binary tree. So first we said that if the root is equal to null, which means we don't have any node in a tree, we are going to create a new node and we make it the root because there's no any node. So the first node will be the root. Else, if there is a node, then we need to locate the parent node. So we assign the root to the current. Now, why the current not equal to null, which means we have elements or we have a node in the tree, it's not equal to null. The first thing we check, if the element value is less than the value in the current, then we assign the current dot left to the current. So we go to the left and we assign the new node as a left child because it's less than the root or the current parent. Else, if the element value is greater than the value in the current dot element, which is the parent, then we assign it as a right. So we have current assigned to parent, then current dot right to the current. Else, false. Else return false means we already have the element. So here, the condition here means either the current value is less than the parent or is greater than the parent. Another option will be is equal. But if it's equal, we don't need a duplicate, so we return false. Now, to create a new node and attach it to the parent node, we check if element is less than the parent dot element, then we assign the new node as a left child of the parent. Else we assign the new node as the right child of the parent. Then we'll return true. So that's again the algorithm to insert an element to a binary tree. Now we can see the tracing here, inserting 101 into the following node. We are going to insert 101 into the following tree, excuse me. So here we check if root equal to null. It's not. If it's not, then locate the parent node. So we assign root to the current. So that's what we are doing here. We assign root to the current. Now we say why the current not equal to null. Now, if the element value is less than the value in the current dot length, which we're going to insert, is 101 less than 60? No, because 60 is our root. We are inserting 101. Is 101 less than 60? No. So which means we are not going to make it as a left child. We move here. This condition is true. The current value 101 is greater than 60, which is the root. Okay, if that's the case, we set it as the right child. So we can see we're going to bring the 101 as the right child. Now, if there's a duplicate, we don't insert. So the next thing we check now is that why the current not equal to null, because here we have 101, so it's not equal to null. This is where our current is now. It's not equal to null. Okay, so if it's not equal to null, but we say 101 is greater than 100, that's what we are checking here. If the element value is less than the value in the current, the value in the current now is 100. So this condition will not hold. We check the second condition. The element value is greater than the value in current. Yeah, that's true. 101 is greater than 100. So if it's that, then we are going to use 101 as our right child. So we go to we'll stay on the right. Now we're going to compare the same thing the new element again, if the current not equal to node, so this is not, if for example, 100 doesn't have a right child, like we can press the 101 here. That's what the condition we are checking, but this condition is false, so we have to go to the next. Is 101 less than 107? Yes, it's true. So if 101 is less than 107 and it's true, then we need to set 101. We assign it as a child, left child. And then we say current is null now, because right now we are here, 107, there's no child. So if it's null, then we say, okay, we are going to create now our condition old now, so we need to create a new node. So if element is less than parent.element, 101 is less than 107 is true. So the new node we are going to create will be the left. So that's here, left. And then we'll return true. So again, that's the concept of the whole algorithm. I want to insert 101. I will compare 101 with the root. First of all, I'll check if there's nothing in the tree. If there's nothing, then my first node will be the root. If there is, I'll compare. It's 101. Yeah, 101 is greater than 60. So we go to the right side. Then we are going to compare. Is still 101 is greater than 100. So we still go to the, if it's less than that, we'll go to the left. We still go to the, now is 101 greater than 107? No. So that means from 107, we go to the left to be a left child. If it's greater than 107, we go to the right. And when we reach right, we are going to set in there because our current is equal to null. So we come out, create a node, and set it at the left. Now let's try this. We are trying to set 59 into the tree. So the same concept. First, we check again if 59. If our tree is the root is null, it's not. So if it's not, we compare 59 with 60. Okay, this time 60 is greater than 59. So we go to the left side. Then we check on again. We check if the 60 have a left child. So we check if it's null. It's not null. Okay, if it's not null, then let's compare the value we want to set 59 with 50. Okay, 59 is greater than 55. So we go to the right side. And when we go to the right side, we check if it's null. It's not null. We have 57. Okay, if you have 57, compare 59 with 57. It's greater, so it will be a right child. Now, when we reach here, there's a null. So we stop. If it's null, we stop. We create a node for 59 and we set it as a right child. Previously, we have 101 left child. So we also have what we call the tree traverser. We have 4 different ways that we can go through the trees or visit all the node in the trees, which tree traverser is process of visiting each node in the tree exactly once, only one time. So we have the in order, pre-order, post-order, depth first, and breadth first traversers. In order means we will go to the left subtrace first, then we come to the root, then we go to the right subtree. Pre-order means we go through the root first, then we go through the left, then we go through the right. Post-order means, again, we go through the left and the right subtree before the node. And depth first means we visit each node level by level. And so let's start with the first one. The in-order transversal, again, is to visit the left subtree of the current node first recursively, then the current node itself. Then the current node will be the root node. And finally, we go through the right subtree of the current node recursively. And the post-order means we visit the left subtree first, then we go to the right subtree of the current node, then finally we come to the current node itself. And that's why it's called post-order, which means we go, the current node will be the last, which is the current root node. And in order means it's between. So we go through left before the current node, then the right. Then next is the pre-order. So pre-order means pre. So we have to visit the current node first. Then we go through current node first. Then we go through the left subtree. Then we go through the right subtree. So let's see an example here. So here we say, for example, and also the breadth first transversal. As we said, we have to visit the nodes level by level, which means I'll go through 60, 55, 100, 40, so we go level by level. So let's see an example how the whole concept will work with this tree. So here we say, for example, in the tree above, let's say the in order. In order means we start with the leftmost, so we go through 45, then we go through 55, then 57, we finish with the left. Again, 45, 55, 57. Then we go through, again, this is in order. And after we go through 45, 55, 57, here again, we should have 59 down on the right, so 59. After that, we go through the current. Again, and the 57 have one right child. So that's why we have the right child is 59. It doesn't show here. Then when we go to the current, which is 60, then we go to the leftmost on the right side because that will be the lowest. So we go through 67, then 100. And also remember 107 have one left child, which is 101. Then we'll go through 101, then 107. And this is the example of the tree that we are visiting now. So you can see we go 45, 55, 57, 59, then we go through 60. Then we go through the right subtree. Right subtree, we start with the leftmost, so we go through 67, 100, 101, then 107. So the next now is pre-order. So pre-order means, actually, sorry, let's go through the post-order first. So post-order means we have to go through the left subtree and the right subtree before the current node, which is the root. So we have 45. And then again, remember we have a right child for 57. So we go through 45. Then we go to the rightmost 59, then 57, then 55. Then after 55, we have to go to the right subtree, the leftmost, which will be 67. Then we have, again, remember we have one left child, 101 for 107. So we go through 101. Then after 101, we go through 107, 100. Then we visit the current node, the root last, which will be 60. So that's the post-order 60. Now the pre-order means go through the left first again. Go through the root first. So we have 60, then we go through the left. So it will be 60, 55, 45, then 57, then 59, then 100, then 67. We don't have no left child on the 67, so we have to go to 107. 107 have one left child, 101, then go through 101. Now, breadth first transversal is more straightforward. 60, 55, 100, 45, 57, 67, 107. Again, breadth first transversal means we go through the node level by level. So that's the whole concept of the three transversal, the four different methods. Again, pre-order means go through the current first, then left subtree, then the right. Post-order means go through the left, then the right before the current, which is the root. Then in order means go through the left, then the root, then the right. Breadth first means go through level by level, level 1, level 2, level 3. So this is the concept of, again, the tree interface. We are using the java.lang collections. So these are some of the operations that we can perform on the trees. We can set a binary search tree. We can search an element. We can insert an element. We can delete. And we can transverse as a in order, pre-order, post-order, And also we can get the size, to get the size of the tree means the number of nodes we have. We can also check if the tree is empty. We can create everything, delete all the items in the tree also. So here we say the size return the number of elements or nodes in the tree. Print the node in post order and pre-order in order transversal. So we can see the code here. Again, this is just the interface. So we import the java.util and collection. We have the public interface. Our class name is 3. Then we extend it to the collections, which is the java.util package. And here we say we are going to return true if the element is in the tree. So we search a method return true if we have the element in the tree. Then insert means we are going to set element E into the binary tree, and it will return true if the element is inserted successfully. The same thing applies to delete. And we delete an element in the tree. We can delete element in anywhere in the tree. Also, we can get the size, which means return the number of elements in the tree. Then next we can do our in order transversal, then post order transversal, and pre-order transversal. We can also check if a tree is empty. We can also check if an item contains, so this means we have to call the search method to know if an item contains in the tree. And we can also have hard method, that is to insert, remove, we call the delete, and also size, we call the get size method. And then we have the contains. All this we check if we have all elements. Again, we are doing extension, the high inheritance of Java collections. So these are some of the methods. Again, in the lab work, we are going to implement the concept. For now, our main goal is the theory. So we have the binary search tree class, which we can see the previous one, the binary tree class. And so see, I went forward. So like I'm going forward. So we haven't reached delete yet. Okay, I'm going forward. Okay. So I want to show, okay, so this is what we went through. So this is our tree class. So what I want to explain here is that the binary search tree is going to inherit everything from binary tree class, because again, a binary search tree is the same, it's a binary tree. Why we call it a binary search tree? The search tree because they have special property that make it possible to search an element, how the values are stored in the tree, like everything on the left will be lesser than the root, everything on the right will be greater than the root or the parent. So here also we implement it, and basically we just inherit everything. So we can see the interface here. We have the BST stand for the binary search tree, implement the tree. And so we have the root. We are using protected because so that this class can directly access the tree class. The tree class will be the parent, BST will be the child. So we have the constructor BST, and we have also the search. Here the search code is written, as we said earlier. So I won't go through this code, the same thing as the slides. We check if there's an items in the binary search tree. If there is, then we are going to again compare the current with what we want to search. If it's less, we go through the left. If it's greater, we go through the right recursively. Otherwise, if it's equal or we cannot find it, then and we come out. So this is our insert method. Again, we're going to do the lab work on this. And basically, this is how we implement the post order. So post order is more or less a recursive function. It's a recursive function because it will visit the left subtree recursively, the right subtree recursively. And then the root post means we go through the root first, then we visit left and right. And also we can see the in order. In order means we recursively visit the left, then we go to the root, then recursively visit the right also. So using a binary tree here, we say we are going to write a program that will create a binary tree using BST, our binary search tree class. We are going to add the strings into the binary tree and transverse the tree in order, post order, and pre-order. So let's see the test program here. So this will be our main method. We are using again the BST class. BST class again inherits BT class or the binary tree class also. So the first thing we do, of course, in the main method is to create our tree. So here we insert, first of all, our tree name is called tree and it's BST. So this is a binary search tree. So this is almost like our homework example. Our homework said we should test our tree after we create the method to swipe the trees or to count the number of nodes in the tree. And actually we have the method here also. So we create our tree name tree. We insert a lot of things. Again, this is string data types. So we insert George, Michael, Tom, Adam, Jones, Peter, and Daniel. Then next thing we want to do is just to transverse through the tree. So we do an in order. We print it, then we do post order. Then we also do the pre-order. Then after that, we are going to search for an element. We already have the search method. So we are searching if Peter is inside our tree. And I think we have a Peter. Yeah, we have Peter. And then we want to get a path from the root to Peter. So let's run this program and see if it will work for us. So we can see the output here, it didn't work. Let's compile it again. Okay, so it compiled successfully. And we can see the output here. In order transversing, post order, pre-order. And then the number of nodes we have is 7. We have 7 elements inside. And also we have the diagram. So this will be our output after we finish. So when we do, this is the tree we created. So in order means we will go through Adam, Daniel, then we come to George, then we go to the leftmost, which is Jones here. After Jones, we go to Michael, then we go to Peter before Tom. Now, post order means we go left and right first. So we go through the leftmost, Daniel, then Adam, then Jones, then Peter, then Tom, Michael, and then George. Post means we go to the root last. Pre-order means we start with George first. Then we go the left, Adam, Daniel. Then after that, we go through Michael, Jones, Tom, and then the Peter. Now, next, we're going to talk about deleting an element in the binary search tree. Deleting, we have to be careful. There's 3 conditions. Now, if we are going to delete an element in the binary search tree and it doesn't have no children, it's easy. Just, or is the leaf, then just delete it straight, everything fine. But when you have one child, we have to be careful because we may select a new root. And then when you have two children, we have to be more careful because we have to select new root. And so here we say to delete an element from a binary tree, you need to first locate the node that contains the element and also its parent node. Now we let the current point to the node that contains the element in the binary tree and parent point to the parent of the current node. Then the current node may be left child or the right child of the parent node. So there are two cases to consider. Case one, the current node does not have a left child, as shown here. Then that's very simply connect the parent to the right, that's it, of the current node, as shown here. So in this case, I just delete, and we see about our parent as there. But the next option, here we want to delete node 10, but node 10 have one child, 16, or the right child, 16. So here we say connect the parent of node 10 with the right child of node 10, I'll show you figure. So if I donate, since you have only one child, if I take 10, then 16 will take over, as we can see here. The 10 is gone. Now the next case, we say the current node has a left child. Let the rightmost point to the node that contains the largest element in the left of the current node, and the parent of rightmost point again to the right node of the rightmost node. Let's see this diagram here. So in this case, we want to delete an item here. So delete a binary search case 2. And then we have the right subtree, we have the left, and this is our current. So current may be left or right child of parent, and also current point the node to be deleted. So if we are going to delete, the content of the current is replaced by the content by the content of the rightmost. So we can see at long last, we want to take rightmost 16. If we take 16, then 14 cannot be a left child, because if 14 is a left child, remember 14 should be less than 10. But 14 can be the right child. And also you can see that when we have the rightmost at 16, we are delete, in this example here, we are going to delete 20. So if we are deleting 20, 20 have two children. So the rule said we should take the rightmost on the left side to be the root. Then if 16 becomes the root, now for example, if I want to delete 10, if I delete 10, I can use 16. I can use 16 as the root. It's only one child. And then 14 is perfect. 14, if I use 16 as the root, 14 should be less than 16. So 14 still left, that's it. But now if I want to delete 20, the rule said take the rightmost on the left side. So we take 16 to be the root. But when 16 is the root, 10 is left, is okay. But 14 cannot be left. So in this case, we have to make 14 as the right, and that will be fine. The goal here is that you can see we take the rightmost if we are taking the root. Then we have to rearrange it to meet the properties of Bst. So this is another example for the root again. We want to delete this node, George. Now to delete George, again, this also, since it's a string, we are going to use the letters. For example, A is less than B, Z is greater than Y, etc. So you can see this binary tree, George. To the left is Adam because A comes before G. But to the right is Michael because M is greater than G. G comes before M in the alphabetical order. So when I'm in M, J become left because J comes before M. T, of course, M comes before T. Now P is less than T because P comes before T. So this works the same way as BST in alphabetical order. So here they say we should delete this node George. So remember we said that when we are deleting the root, we should go to the left side and take the rightmost. So we are going to use Daniel as the root. Now when we put Daniel as the root, since again, Adam have only one child, it's more easy. In this case, we finish. And the tree still the property of BST. So another example, we delete Adam. If we delete Adam, Adam doesn't have no children, so that's it. The only thing in our next lectures, we are going to talk about how to rotate or how to convert, because right now what we have is like an unbalanced tree, unbalanced. This is unbalanced tree, so we have to balance the BST. The goal of balancing a tree is to optimize it, to make it more faster. We will discuss this again in the different lectures when we cover the rotation and FVL. Normally, if you're going to balance any binary tree or BST, we have to do some rotations, left rotation, right rotations, etc. So now we want to delete this node, Michael. Now we have to be careful here. When we delete Michael, remember that on the Tom is greater than Michael. So by the algorithm, we have to use the left child. And also the left child doesn't have no children. So we have Jones as the root, which will work fine because when Jones become a root, Tom is greater than Jones. So it stay at the right, and Peter stay where it is also. Now the next is the binary tree term complexity. As we said earlier, the transversing in order, pre-order, post-order is big O N. The reason why it's big O N because we have to N is the number of nodes we have in the binary tree or binary search tree. So we have to visit each node. So it's big O N. Since each node is transverse only once. Now the term complexity for search, insertion, deletion will be the height of the tree. This is very important. In a worst case, we have big O N. That's why we say we have to balance the tree. So you can see that the higher the height, and the longer it is. But if the height is less, then we do a less visit. I mean, if the height is less, then the searching, insertion, deletion will be lesser. So that will be the conclusion of our lectures. Before that also, let's look at the test for Bst Delete. Previously, we look at the code for the insert. So the same concept, we have the main method. We create the same tree again. And then we do our delete. So again, we have the method already delete. So we say tree.delete again, our objects and the method. The object we create here is tree. So if I want to use any BST method, I have to refer tree.delete. And now deleting George, then we can print the tree. We may see the output. So the same thing, I can delete Adam. We also delete Mike. Anytime we delete, we print the tree to see how the output will look like. And this is the method to print tree. So we can also use the in order, post order, pre-order, etc. Go to print a tree means we're going to print all the nodes. So we can go through the node in 4 different ways here, either in order, post order, pre-order, or again, breakfast. We also check the size of the tree, which is the number of elements in the tree. So that will be our conclusion for these lectures. And again, wish everybody the best and thank you for your time.